everybody. We continue our long journey into mathematics, and actually we are talking today about a very important subject, which is polynomial identities. In some textbooks it's called binomial products, like in this one, for example. Here are the formulas nicely written, and those are the formulas I want to concentrate on. First of all, let's prove them. We can prove them very easily by just multiplying out. Let's do that. The first one, the so-called square of the sum. It's just a plus b squared. By definition, it's a plus b multiplied by a plus b. Then I just multiply out. To do that, I have to multiply every member of the first expression by the whole second expression. And then it's a squared plus ab plus ba plus b squared. But then we remember that there are such things as like terms, which tell us that those two terms are actually the same. It's true we have different order, AB and BA, but we know that when we change the order in the product doesn't change. So what we have here is actually a squared plus AB plus another AB plus b squared. And finally we can reduce the expression adding together all like terms. This is the final result. A squared plus 2ab plus b squared. The same thing happens when we prove the second expression. A minus b squared, it's actually by definition a minus b times a minus b. And we do the same thing again. Bad luck. Here we go. A squared minus ab minus ba plus b squared. It's a plus because it's negative b times negative b, the last term. And again, as before, we have two like terms, and they add up to give us a squared minus 2ab plus b squared. So when you memorize this, you remember that this plus goes here, and this minus, it goes here, in front of the double product of the two quantities. And finally, the last formula, which is maybe the last but not least, maybe it's the most important, at least it's mostly frequently used. It's already in the form in which we can easily multiply out. It's a times a minus b plus b times a minus b. So a squared minus ab plus ba minus b squared. Again, we notice the same cross terms, like terms. Actually, they are the same. Minus one thing plus the same thing. We know that it cancels. And we arrive at the final result. Very important. But can I somehow prove that it is really important. First of all, it is on our curriculum list, but on the other hand, it's stupid to mention the school curriculum. It's true that schools usually give us important things, but something more practical. My practical example would be those formulas are very useful when we want to calculate without using a calculator. As you know, sometimes and now and again in exams we are asked not to use our calculator. For example, imagine that I am trying to use a Pythagorean theorem for a triangle with two legs. One is five, one is Pythagorean triples. I'm in a bad form today. Okay. 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 Today is the day when I remember only one Pythagorean triple. I was unsuccessfully trying to remember, but somehow it's not my best day. The thing is, I remember is 3, 4, 5. 3, 4, 5. Of course, this example is not very impressive. Yeah, now I remember it. By the way, what I've just shown is that when we are trying to remember something, we have to, if we can't, like I couldn't 30 seconds ago, just try remembering something easier, related. And exactly after writing down my favorite Pythagorean triple, I remembered what I wanted to use. This one. It was my mistake. The second one, 7, 21, and something else we can calculate later. This one is already much more complicated. So imagine I am trying to calculate one leg, for example, this one. Let's pretend that I don't know it. And using Pythagorean theorem, I should write that 13 squared equals x squared plus 5, which gives me x squared equals 13 squared plus 5 squared, of course, minus 5 squared. Which in turn gives me x is equal to a square root from 13 squared minus 5 squared. Yeah, it's true, it's not very difficult to multiply by hand to find those squares. Maybe somebody remembers those squares like I do, I remember. But what is the most useful thing to do is to use this last formula. I see the difference of squares. It's also called the difference of squares. A squared minus b squared is the difference of squares. And I know that it is the same as 13 minus 5 times 13 plus 5. This is much simpler. 13 minus 5, it's mental arithmetic. It's, what is it? It's 8. And 13 plus 5, it's also mental arithmetic, is 18. Still, I know that I can't take a square root from 8 or 18. But what I have is factorization. I can factor them down to things, two numbers which I can take square roots from. 8, I know it's 4 by 2. And 18, it's 9 by 2. And what I see now is that there is a 4. So it factors out. I can take a square root. It gives me 2. There is also a 9. It means that a 3 goes out from the square root. And what I have, what is left, is a pair of 2's, which gives me finally 2 by 3 by 2. And that's exactly 12. This example, again, is not very impressive. But in reality, when you find something, what I was trying to memorize, to recall, the last one, this leg should be 7, this should be 21, and this should be something else. Let me show you something. I'll use another formula to calculate, to simplify my calculations. Again, I want to apply Pythagorean theorem to this triangle to find x, hypotenuse. 7 squared plus 21 squared. And I remember that 7 squared is just 49. But what about 21 squared? Of course, I can always perform long multiplication, but I'll do differently. I'll write that 21 is 20 plus 1. And then I apply the first formula from the set, a plus b squared. This will simplify things greatly because everything becomes mental. Mental arithmetic. Look here for yourself. 20 squared plus double product, it means 2 times 20 times 1, plus 1 squared. 20 squared means 400 exactly. 2 by 20 means exactly 40. And 1 squared means exactly 1. It's 441. Here we go. And then we arrive at 441 plus 49. It's not a perfect square. That was my mistake. Yeah, that Pythagorean triple isn't. I think it should be hypotenuse. 441 plus it's 490. 490 square root from anyway we succeeded because I calculated my x. X is a square root from 490, which gives me a square root from 49 times a square root from 10. And this is 7 square roots from 10. That's it. Nothing else. I think it should be okay. I'll have to study Pythagorean triples next time. That was not my goal, not my actual goal. My final goal is to tell you about this beautiful woman, extraordinary woman, absolutely. I know that in Russian her name is pronounced Sophie Germain, and from what I can understand here, in French we shouldn't pronounce the final N, Sophie Germain. But anyway, she was a French mathematician, physicist, and philosopher. This is unusual for a woman. And she lived at the same time as Leonhard Euler, Lagrange, Legendre, and Carl Gauss. And she communicated with all of them. I'll put a link, but you can easily find it in Wikipedia. I'll put a link onto here. And among her other remarkable achievements, there was an identity, a polynomial identity, which is widely used in Olympiads. And we can actually prove it now. Here it is. Here it is. Where is it? Yes. Here it is. Here it is. And we can prove it now. And we can prove it now. Actually, our proof would be, as you see, it's much more complicated than those we've just considered. That beginning and that end are of greatest importance because actually this form is rarely used. It's just now I regret putting those things. Okay, here I go. My talking face will go here. How do we prove this identity? We can actually multiply out. We can actually multiply out the final product. As you see, it begins x squared plus 2xy, like this is a part of x plus y squared, and this one begins like x minus y squared and plus y squared there and there. So let's multiply out the last one. X squared plus 2xy plus 2y squared times x squared minus 2xy plus 2y squared. Actually, we have to multiply 3 times. The first term here plus 2xy times the same and finally something awkward, 2y squared, and finally 2y squared times the same, x squared minus 2xy plus 2y squared. Let's go. X to the power of 4 minus 2x cubed y plus 2x squared y squared plus 2x cubed y minus 4x squared y squared plus 4x y cubed plus 2y squared, let me put x first, 2x squared y squared minus 2x y cubed, and this in this case it's 4. It was my first attempt to make a mistake. 2 by 2 it's 4. And plus finally 4y squared. Let's have a look at the like terms. Let's underline them. The first one, x cubed y. Let's go through all of them and find the like terms. This one is the same, x cubed by anything else. We don't have any x cubed. And we see that this cancels. The second one will be underlined like that. X squared, y squared, where is the same thing? Aha, here it is. Anything else? Aha, here. We see 2 plus 2 plus, just a second, 2 plus 2 and minus 4. So the quotient is 0 because 2 minus 4 gets me minus 2 plus 2. So that also cancels. And finally, by double lines, I underline y cubed, and I see that they also cancel. And I arrive at the final result. A beautiful symmetric, this expression is symmetric. And we just have to remember when we see this structure that it can be factorized like this, and everybody who is trained for International Mathematical Olympiad knows this, studies this, uses this into in his practice. That's all I wanted to say. See you next time. I promise to memorize some other Pythagorean triples by that time.